Okay, is my screen and my voice audible to everyone?
Yeah, audible, sir.
Yeah, okay. Welcome you all to the sixth week of our live session. So, last week we were predominantly dealing with two types of heat exchangers. One was plate fin heat exchanger, and the other one was different kinds of finned tube heat exchanger. So today's topic of discussion would be mostly related to plate fin heat exchanger and the design aspects of it. So uh, I'll take you one step back from where we started previous week's discussion. So this is how a plate fin heat exchanger looks like. There are different passages for different fluids. This is a two-stream heat exchanger. I mean, two different fluids without mixing transfer heat between the interacting fluids. So this is a transfer type heat exchanger. So unlike our cooling towers where direct mixing happens, we are only dealing with transfer type heat exchanger. Of course, this what you see on my screen is a two-stream heat exchanger. Obviously, with proper designs of headers, we can accommodate multiple streams, three-stream heat exchanger, four-stream. So they are called multi-stream heat exchangers. So if you see this heat exchanger, it is a cross flow heat exchanger, meaning that one fluid is at 90 degree with the other fluid. So based on this discussion, uh, uh, we are interested to find out the performance of fins on different plates. So what is the effect of attaching these plates on the fins is what the main agenda of today's discussion is going to be. So from our previous NPTEL lectures, we have this week's NPTEL lectures, we have learnt that the temperature distribution along a plate fin with respect to length is given as T of X is T of A, where A is our temperature at the base times 1 minus sigma into e power mx plus sigma times e power minus mx, where sigma is defined like this. So if one plate is at temperature Ta, what I mean is assume that this is at temperature Ta and this to be at Tb. So if I am interested to find out the temperature distribution along these plates between two interfaces, that is Ta and Tb, this is how my temperature distribution is going to look like. This is already a known point. So from this point we are going to start solving numericals today. So I would encourage you to look at my screen and solve this particular problem. It is not a difficult one. In the analysis of a multi-stream plate fin heat exchangers, the condition for temperature extremum to exist is, so we know the temperature distribution from my previous slide. So based on that temperature distribution, what is the condition for extremum to exist? So extremum means we know that either temperature minimum or temperature maximum. We can take a couple of minutes. Any ideas how to approach this problem? Okay. Uh, so this is a temperature distribution profile. So to find out the condition for temperature extremum, we do differentiation obviously. So dt by dx should be equal to 0, where x is the length of the fin. So and equate it to 0. Can you take a minute and try it? This is the temperature distribution. T of x is, you can take T of x or theta of x equals theta a into 1 minus sigma into e power mx plus sigma times e power minus mx. Shall I show you the solution? Okay. So as I have told you that for extremum temperature, that means temperature minimum or temperature maximum. I'll just get back and show you some significance of this. I have already discussed that this temperature is at TA and this temperature assume that to be at TB. So we are interested to find out that position of the fin along the fin where a temperature minimum or temperature maximum happens. So that is the point of discussion in finding out. That's the point of discussion in doing this exercise. So for finding out temperature extremum, we are obviously going to differentiate that with respect to x and equate it to 0. So once you do that, you get to this expression e power 2 mx equals sigma by 1 minus sigma. So differentiation is not difficult because it is in terms of E, and other quantities like theta A is constant, sigma is constant. So we only have e power mx. So once you differentiate this theta of x with respect to x, uh, the differentiation is also easy. We end up with having this expression. So where sigma is nothing but e power ml minus r by 2 sin hml. This h is hyperbolic function divided by 1 minus sigma. So we end up having e power 2 mx equal to e power ml minus r divided by 2 times sin hml minus e power ml plus r. So we'll go back to the definition of hyperbolic sine function. So it is defined somewhat like this. Its definition is this: sin hml is defined as e power ml minus e power minus ml by 2. So sine hyperbolic of x is e power x minus e power minus x by 2. So once we plug this value into equation 1, the rest is simple. E power 2 mx equals e power ml minus r by r minus e power minus ml. So this is the condition where temperature extremum can exist. So this is the value of x where it will happen. Any questions here? Okay. If there are no questions, we'll go further. It is related to the previous problem only. In the analysis of a multi-stream plate fin heat exchangers, if a temperature extremum exists and R equals cos H ml, then can you find out that condition of X where this holds good? Can you find out the value of X where R equals cos H ml? So because temperature extremum already exists, so you can start from this point already. E power 2 mx equals e power ml minus r by r minus e power minus ml. So that case is already given to us, and the value of r is also given. I am interested to find out x. Any answers? You can unmute and tell if you have any concerns too.
X equals to 0.
Okay. We have one answer. X equals 0 is one answer. Uh, are there any other answers? Okay. So we know that temperature extremum already exists. So e power 2 mx will start with this point directly. So this equation directly, the previous equation. So given that r equals cos hyperbolic cos h ml, we'll plug the value of cos h ml into this function as r and give the definition of hyperbolic cos ml. So cos hyperbolic x is defined as e power x plus e power minus x by 2. So once we know this definition, we are through. Just plug the value of cos HML into this equation, uh, and the rest is just arithmetic. There should not be much of a concern. So we'll end up with final expression being e power 2 mx equals 1. So since m is already given to be greater than 0, that is fin parameter, so the only remaining condition which can satisfy this equation is this one. That means this is equal to e power 0. So 2 mx should be equal to 0. That means x should be 0. The person who got x equals 0, have you followed the same strategy, or have you do you have any other different idea?
Yeah, same thing, sir.
Okay, fine. Any concerns here? Okay. We'll go to the discussion where heat exchangers are classified are qualified. So based upon heat transfer and pressure drop characteristics, we say that this heat exchanger is better than the other heat exchanger. So say that we have one type heat exchanger where the air enters in the core of a plate fin heat exchanger as shown. I'll show you the next figure too at 1 atmosphere and 30 degrees Celsius. Some fin parameter, namely sigma, is also given 0.494 and hydraulic diameter 0.4 centimeters is also given. The mass flow rate of air is 1500 kg per hour. It is in cross flow direction with a mean temperature of 100 degrees Celsius exit temperature. The core of this heat exchanger is about 0.5 meter long with 0.25 meter square being the frontal area. The other quantities like Prandtl number, density, Cp values are all given. Uh, this is the chart giving F versus Re and Stanton number into Prandtl number power 2 by 3, that is nothing but Colburn J factor, that's called Colburn J factor, that is also given with respect to Reynolds number. So remember this is Reynolds number in terms of thousands. So zero point 0.6 in the sense it is 600, zero point 0.8 in the sense it is 800 Reynolds number and 1000 Reynolds number and so on. So we have a finned tube heat exchanger, the diagram of which is given here. We are interested to find out the pressure drop of air, that is delta P inlet minus delta P exit. I mean P inlet minus P exit, that is delta P. You can take time, this will take time. So in my previous discussion I told you that there are four causes of pressure drops. The first one is pressure drop due to contraction, area contraction, frictional pressure drop, momentum pressure drop, and pressure gain due to expansion. So out of these four, the first and last can be neglected. The pressure drop due to area contraction and pressure increase due to area expansion, that can be neglected, and two pressure drops we have to consider, that is frictional pressure drop and momentum pressure drop. Frictional pressure drop happens because obviously the air is passing through tubes which have corrugated surfaces. They are not smooth, perfectly smooth. So there will be a drop in pressure. And the second term, that is momentum pressure drop, that happens because of change in density. At the inlet the density is different and the exit the density is different. So as a result there will be a pressure drop. So that's called momentum pressure drop. Of course there will be gravitational pressure drop too, but this is in a horizontal direction, so we neglect gravity pressure drop. So only first two terms on pressure drop are considered, the frictional pressure drop and momentum pressure drop. Yeah. For those who want a little help for the starting, you can take this. Delta P total is delta P frictional plus delta P momentum pressure drop. So these are the formulae for frictional pressure drop and momentum pressure drop. I'll leave this here for you to try uh, for a couple of minutes or so or more, uh, and then you can, and then I'll show you the solution. I suggest you to calculate each of these quantities separately. Mass flux G, rho inlet that is given, AT by A minimum that we are going to get from the data given. So I suggest that you should go step by step before plugging the final answer. Okay, any answers for G, mass flux? I want the first term which I want to proceed further is G. Okay, I'll show you how we calculate G. So G is nothing but m dot by area minimum. So m dot is given as 1500 kg per hour. So I want to convert it into seconds. So I divide it with 3600, and area minimum, that is nothing but fin parameter sigma multiplied with the frontal area. So frontal area is given as 0.25 meter square in our question. Sigma fin, one of the fin geometrical parameter, is given as 0.949. 0.494, and 0.25 meter square being the frontal area. So once I get sigma AF, that is 0.124 meter square, I am ready to go with finding out G, that is 3.36 kg per meter square second. Okay, so once I find 3.36 kg per meter square second, the next target is to find out AT by A minimum. So AT by A minimum is nothing but 4L by hydraulic diameter. The length of the heat exchanger is already given, 0.5 meter long, and hydraulic diameter is also given. Once we plug the values, we get AT by A minimum as 451.5. So once we get that, we are ready to find out Reynolds number. Why should we find Reynolds number? Because I don't know one more term F here. So to find out F, I need to either know some analytical expression for finding out the friction factor, or I need to have a chart for this particular geometry which can give me F with respect to some dimensionless number, that is in our case obviously Reynolds number. So I have this chart which describes f with respect to Reynolds number. So once I find out Reynolds number, I am good to find out f. So Reynolds number is nothing but g into hydraulic diameter by mu, uh, dynamic viscosity. This is mu. So g, all the parameter, all the values are known, gd by mu, and once we plug in, we get Reynolds number as 729. So I suggest you, can you find out what could be the approximate value of f for a Reynolds number of 729? This is the curve for f, and x-axis is on Reynolds number. Okay, so this is zero point 0.7, that is Reynolds number corresponding to 700. So 720 is somewhere around this mark. So I traverse vertically upward for 729 and find my Reynolds friction factor here. So it is approximately 0.057058. So you can take a pencil, and once you have graph in your chart, graph in your hand, you can obviously interpolate it well, within very less, with very high accuracy. So you can take it to be 0.057. So once the friction factor is 0.057, AT by A minimum is also known. Rho inlet, that is density at inlet point, that is also known. Density at exit is also known. So what is this rho? This rho is the average density that we are going to take at bulk temperature, that is not equal to rho I, that is not equal to rho O. If the fluid is incompressible, that means if rho I is equal to rho exit, as we have seen one problem in our previous session, rho I was equal to rho exit, but here that is not the case. The density at inlet and density at outlet are to be considered. So I calculate rho as the harmonic mean. So rho is given as 1 by 2 of 1 by rho I plus 1 by rho O whole to the inverse. So it's an harmonic mean. So I get rho as 1.054 kg per meter cube. So this rho value I am going to plug it here. Can you please find out what total pressure drop is now? All values are known. I'll just give you half a minute to try and see if you are getting uh, pressure drop in reasonable limits. So once we get the values of all the quantities which we require, it is just a we just need to plug the values. G square is known by 2 times of rho inlet. Rho inlet is also given. So into friction factor times AT by A minimum into rho I by rho. All other quantities are also known into 1 minus sigma square rho I by rho O minus 1. So we get a pressure drop about 139 pascals. So this is fairly a small pressure drop, 139.14 kilopascals, because the operating fluid is in vapor medium, that is air. So 0.14 is a reasonably small pressure drop. Any questions up to this point? How to find pressure drop? Okay. If there are no other questions, we have one more task. We need to find out the average heat transfer coefficient of air. As a hint, I'll tell you that we have friction factor F and we have Colburn J factor. In the Colburn J factor, we have one term called H, that's the heat transfer coefficient. The other quantities are all already evaluated by us, GCP into mu Cp by K. Can anyone tell what this quantity mu Cp by K is?
Prandtl number.
Yeah, it's a Prandtl number of air. So mu Cp by K Prandtl number is already given. We just need to Prandtl number is already specified 0.719 for air. So we just need to specify. We just need to find out H value. I'll give you a minute or so. You can try peacefully and tell the answer. Okay. Do you need some more time to try, or shall I show you the solution? We already know the Reynolds number, so it is 729. So based on this graph, similar arguments hold good for friction factor and Colburn J factor. We either have to resort to a numerical expression given which involves heat transfer coefficient, or these graphs are more reliable because these are experimental graphs which are conducted over a wide range of Reynolds number. The same argument holds good for both friction factor and Colburn J factor. So once we know the Reynolds number, which is 729, traverse through this 729 vertical line, and wherever we cut this this curve for Colburn J factor, we are going to draw a horizontal line back there. So this we can take it around 0.016, about 0.0165 or whatever. So once we get 0.0165 as Colburn J factor. The other quantities being known, we just have to plug in the values to find out the heat transfer coefficient. So 0.0165 times G is 3.36, Cp is given. We need to be careful while plugging the values with respect to their units. So the Prandtl number is also given 0.719 for air, and the heat transfer coefficient comes out to be 69.56. So this is also fairly reasonable for uh, heat transfer coefficient during forced convection would be somewhere around 10 to 100 watt per meter square Kelvin. It's not a hard and fast rule, but I'm just saying that heat transfer coefficient of about 70 watt per meter square Kelvin is reasonable for air during forced convection. Any questions here? If there are no other questions, we can jump to the next problem. This is a fairly simple problem than what we dealt previously. We have a plate fin heat exchanger where air at 1 atmosphere and 300 Kelvin flows with a free flow velocity of 10 meters per second. Fin geometrical parameter, that is sigma, free flow area by frontal area of is also given 0.4. The hydraulic diameter is given for the passage of air 0.15 centimeters. L by D ratio of 5 is also given. Other properties, thermophysical properties like rho, K, Cp, viscosity and Prandtl number is given. So we are interested to find out the core pressure drop in the heat exchanger. So I'll take one step back. Uh, so this is the pressure drop due to area contraction. This we are going to neglect. This is the pressure due to momentum, change in momentum. So there is a momentum pressure drop. This is frictional pressure drop because we have frictional factor involved here, and this is pressure gain due to area expansion. So even this we are going to neglect. So we dealt with these two terms in our previous problem. So I'll suggest you to take a close look and see. So this expression basically turned into this expression for our previous problem. So I will suggest you to take a closer look and see if the same formula can be applied in this problem too. Remember, we want only core pressure drop. So that's the reason we are neglecting the pressure drop due to area contraction and pressure rise due to area expansion. Do you need some time to try? We'll follow the same steps that we followed in the previous question too. So there is no momentum pressure drop in this problem because rho at bulk temperature is already given. So we can neglect the temperature, we can neglect the momentum pressure drop. So that's the reason I was telling it is simpler than the previous problem. We only have frictional pressure drop here. So frictional pressure drop, we have a factor F, which is already given. In our previous problem, we had to dig in from the graph. So G square by 2 times rho I into friction factor times AT by A minimum into rho I by rho. Even rho I by rho is same, it is 1. So the only thing that we need to calculate is this ratio AT by A min and G. Rest all others are given. Okay. The first step in finding out the pressure drop will be the calculation of mass flux m dot by area minimum. So m dot I will find out in this fashion. M dot is nothing but rho a v from our continuity. So m dot will remain a constant. So rho into frontal area. So if I consider frontal area, I need to take free flow velocity, that is u infinity, that is already known to us. So AF by A minimum, that is nothing but fin parameter called sigma, that is nothing but A minimum by AF is nothing but given as 0.4. So G I can write it as rho u infinity by sigma, which comes out to be 15.39 kg per meter square second. And one more parameter, which is nothing but AT by A minimum, which is 4L by hydraulic diameter. Even that is also given. L by D ratio is given in our problem. So multiply that with 4, we end up with getting 20. So once we have these two values, G and AT by A minimum, the rest is just arithmetic. Plug these values into this expression to find out that delta P is 115 Pascal. Any questions here? Okay. This is more of a normal thinking question, analytical question rather than numerical one. So in the analysis of multi-plate plate fin heat exchanger, multi-stream plate fin heat exchanger, if a temperature extremum point exists within the fin length, then what point is true? The transverse conduction is present. Transverse conduction is not present. It may or may not be present, and we need some more data. What is your comment on this?
Is it C, sir?
Okay, sometimes one of our friends says that transverse conduction may be present sometimes and may not be present some other time. Okay, any other ideas? Okay, so there is something called half fin idealization. I will take such that in a idealized case, I will assume that both temperatures are TA. I'll extend it to a general case. So if these two were at a temperature TA, these two plates at temperature TA, at the midpoint we have something called adiabatic plane. That means this fin is a separate fin. This can be considered a separate unit, this fin, and this can be considered a separate unit. So the same argument holds good all along for all fins. So there is a point where there is no heat transfer happening. So that is the adiabatic plane at the halfway mark. If TA these two are equal, but in general these two are not equal. There is certain other temperature distribution TA, and say that this is TB. So my adiabatic plane also shifts towards bottom or towards a top, given the case that there is a temperature extremum point exists. So there are cases also where if R, that is theta b by theta a less than cos 1 by cos h ml, you can find it in the NPTEL lecture videos where okay, for the sake of discussion I'll draw this, but you can find a proper explanation in the videos. Say suppose this is TA and this is TB. These are the plate temperatures, and assume that I have a temperature T naught. T naught is my fluid temperature. So if there is heat transfer that happens from wall to the plate, I give a direction from left to right or a clockwise. And the same for TB. If there is a temperature distribution from, if there is a heat interaction from surrounding to this plate, I have a situation where temperature minimum exists at some point here. So if TA and TB are equal, I said that the adiabatic plane is exactly at the halfway mark. But if TA and TB are not equal, I have a certain other uh, plane depending upon the temperature distribution. It can be above or below. So there that is a plane where adiabatic tip exists. As a result, there is no transverse conduction that can happen. So given that if extremum point exists inside the fin or within the length of the fin, the transverse conduction cannot be present. So B is the correct answer. If this question is flipped in such a direction that the temperature extremum point may exist outside the fin length, then we cannot say transverse conduction, then the transverse conduction will be possible. So there are two cases, this temperature extremum point, that is the one which we need to take care. Temperature extremum point is within the fin length, then definitely transverse conduction is not present. If we don't have this information, we cannot say. Is my argument satisfactory?
Yeah, yes, sir.
Okay. Uh, For some more problems, you can refer to Shah and Sekulic, and also in our NPTEL videos for week 6, professor was discussing about Case and London book, Case and London 2, heat exchanger design handbook by Case and London. So interested people can refer to that for higher knowledge. So I think we will. One more point. Uh, People were asking me questions on discussion forum. I have started to answer them. Maybe by today evening or by tomorrow I'll be able to answer to all of them. I have given some answers to some questions already. Can we end the session today?
Yeah. Thank you, sir. Thank you.
Okay, thank you.